There are many ways to discretely describe a continuous signal. We have considered three. Fourier series descriptions are 200 years old. Shannon's sampling theory is about 75 years old. Wavelets have been popular for about a quarter century. These times are long on the scale of an individual lifetime, but incredibly fast over the scope of human history. Recently, new ways of representing signals have emerged. The von Neumann model of serial processing is under increasing attack as machines move to ever greater parallelism. This graphic illustrates the analogy between biological neural networks and connectionist machines. The basic idea of a connectionist machine is that information is stored in the structure of the machine rather than in separate memory data structures. Connectionist machines are revolutionizing computational imaging. For example, rather than spend a week generating the graphic shown here, I simply asked DALL-E to generate it. Among other uses, connectionist machines provide a new and potentially more efficient mechanism for representing object distributions discretely. Let's discuss how this works. Computational imaging. Episode 8, Neural Representation. We've seen that we can describe the continuous function f of x using a base set of basis functions phi sub n. F sub n is the expansion coefficients of f of x on this basis. By taking this sum over the basis, we can look anywhere at any value of x and find a value for f of x. So we find f of x effectively with arbitrarily high resolution. This is one way for us to describe a function, but we could describe functions in other ways. For example, I could just say, it's a Mexican hat function or it's a sine function, and you would know what I mean. So we might want to start to generalize ways and think about what other ways could we describe functions. We might want to imagine some kind of box where we could just create a set of algorithms that would generate x, or generate f of x given x. So here we input x, and the output is f of x. This kind of box would be called the universal approximation machine. Here's what DALL-E sketched when I asked it to make a picture of a universal approximation machine. You see, DALL-E knows that somehow we're going to end up with a connectionist machine and made all these connections, and that's what we're going to try to figure out. But we might even think of a machine as looking at something like this, where we have input x, and out we're going to get f of x. This could be some kind of musical synthesizer, for example. We input something and it adds some eerie music based on the setting of these dials. So we would set all the dials in such a way that the output would be f of x. And then the state of the dials would be our discrete vector describing the function f of x. How would we set these dials? Well, people have been looking at building these kind of machines for the last half century, and the basic building block is called a perceptron. So a perceptron is a simple vector matrix multiplier that takes a vector of inputs x, multiplies them by weights w, and then adds those weights to get the state y, and then operates on y with an activation function. Here the activation function is omicron, the Greek letter, and we've taken the sum of x multiplied by the weights and added potentially some bias, and then getting the output y. So for the set of the vector of inputs, we get one value y, and we might want to think about what kinds of values of y could we get. Well, obviously it's going to depend on what the activation function is. When people first thought about these machines, they were thinking about segmenting data sets, and so they used this sigmoid function that has a threshold. So you sum the inputs with some weights, get a threshold, and try to classify the state of the inputs. More recently, people have developed a wide variety of activation functions and shown that they can be useful in a wide variety of different states. So we have all these activation functions, and with each activation function, we can get a different set of outputs. So here's an example where we have a perceptron with two inputs, x and y, let's say. And in fact, we've made a map here of the x-axis and the y-axis. And then we weight each of these into a single neuron and act on it with an activation function to get an output. So the density of each one of these plots is the output. In this case, the weight on x is 0.5 and the weight on y is 0.25, and we've acted on it with the Jalou, sigmoid, sine, and sinc activation functions. And you see we get different distributions in the plane based on which activation function. Also, changing the weights obviously would change the distributions we could get. This gives us a way to generate a new output y from a set of inputs x, but obviously it's not of sufficient complexity to generate an arbitrary function f of x from the inputs x. But we can generalize this to develop what's called a multilayer perceptrons. We use the perceptron as the basic building block, but now we do cascaded layers of perceptrons. And with this kind of architecture, we can generate a universal approximation machine. Here's examples where we take a 3-layer network. We have 2 inputs. So again, we have the X and the Y planes here as the inputs. And then, but then we'll have 256 layers in the neurons in the first layer, and all those weights from the 2 inputs. And then we have 16 layers in the neurons in the next layer, and then 8 neurons in the next layer, and finally 1 output neuron. And what we're looking at here is the density of the output neuron. And we've gone and set the weights randomly in this case, but you see that we can generate relatively complex patterns from this set of 5,772 random weights, and then with those 5,000 weights we get a signal value at every point in the XY plane. Now, we don't want to generate this kind of random pattern. We'd like to use this to represent functions. So we need to train a neural network to generate the functions that we want from a set of weights. And so for that, we use a training strategy. We can use typically a set of inputs. In this case, the inputs could be positioned in the XY plane, and the output we want to generate. And so let's say we want to represent an image with this strategy. We choose a point in the XY plane, and we train the network to generate f of x at that point. So we need a set of examples to train the network with. Here I'm showing the modified National Institute of Standards and Technology database of hand-drawn digits, which is a set of images that we'll use in several examples throughout our discussions to demonstrate neural training. So with this set of inputs, we can generate a neural network. In this case, this is a sinusoidal representation network. So we have a network that we define with layers. So in this case, it's a network with 2 inputs, and then has 16 neurons in the first layer, and then it has 4 neurons in the second layer, and then it has 1 neuron in the output. So we're going to try to train this network to generate a digit from the inputs x and y. So this is our network. The network turns out to have 121 trainable parameters, and we want to use those 121 parameters to generate our image map. You'll notice some things here that we've told the network we want to use a certain optimizer. That's a parameter, a function we're going to use in the gradient descent process of training the network. There's a loss function to tell the network how well it's doing, and then metrics around accuracy that we use to monitor how well the network is doing. So once we've defined a multi-layer perceptron to try to generate this mapping, we want to go ahead and train it. So we won't get into details here about how training works, but basically it's a gradient descent process, and we just go to the TensorFlow in this case and tell the system we want it to train the multi-layer perceptron with the training data set consisting of these digits and generate the output. Now, in this particular case, the training data set is going to be a single digit. We want to train the network to generate what turns out to be the letter O. And so we give it examples of what the output should be at every position x, y for the letter O, and then it's able to generate that. So the image on the left here is the training data set. We're going to train just with this single letter O, and then the image in the center here is the output of the network. When we input the value x, y, what at each position x, y do we receive? And so you see that we've basically trained this network to generate from 121 parameters this image O. Now in this case, the image is 28 by 28, so the number of image pixels is around 1,000, and the number of parameters we've used to describe the function is 121. So we've compressed the data that we were able to generate this 1,000 pixel image from 121 trained parameters. More than that, we can then put into the network x and y with finer resolution than the training data and see what we get. And that's what's shown on the right, that we've generated an interpolation function that takes the training data and generates the original trained function. The quality of the neural representation depends on hyperparameters, the number of layers that we use, the number of neurons in each layer, and the activation function that we choose. We don't have to choose the same activation function for all the neurons or all the layers, but here's an example where we have done that. We've used the Jolu activation function, the sine activation function, and a sync activation function, all trained on this single letter using what we call this positional encoding, the XY value as the input and the image as the output. And you see some slight differences in the quality of the reconstruction. Here's an example of interpolation using the siren network, the sinusoidal representation network, and a sync activation function. And again, you see some difference in the activation. For present purposes, the point is that we have introduced this idea of neural representation of functions and neural regression, that we can use regression in a neural network to represent data. We'll use this a lot in our discussions throughout this set of lectures, and we'll always be interested in ways to turn the knobs and recover the data.